Hello. In this episode, we will look at our first example of exact first order differential equation. So remember, any exact first order differential equation, when written in this way, m plus n y prime equal to 0, by definition, the following must be true. So this is how you check that a first order differential equation is exact or not, which we went over in the last episode. So how to check before you try to find the function phi, how you check? You have to check that the partial of m with respect to y is that equal to the partial of n with respect to x. So in this example, this is my m and this is the n. Remember, n you have to include the sign. That's very important. In this case, it is plus, so it does not really matter. But if it is a minus, you have to include that minus sign also as a part of n. Here, so let's actually write that down. So maybe I write it down below. So in this example, m is 3x squared minus 2xy plus 2. And the n is 6y squared minus x squared plus 3. Let's check. So the partial of m with respect to y. So y is the variable. So 3x squared is 0 because x is like a number. The derivative of negative 2xy is negative 2x. That's like a number. It's like the derivative of 5y is 5. So the derivative of negative 2xy is just negative 2x. So negative 2x is like a number. Plus the derivative of 2 is 0. How about the partial of n with respect to x? So here x is the variable, y is like a number. So the derivative of 6y squared is 0. The derivative of negative x squared is negative 2x. And the derivative of 3 is 0. So indeed, you can see that they are equal. So they're equal to each other. So indeed, it is exact. So now we can go ahead and find the function phi. So if at this point, if I get negative 2x and something else, which are not equal to each other, then we have to stop and say that this differential equation is not exact. So we cannot solve this way. We have to use some other method. But right now they are exact. So how can we find the potential function phi? And there are two methods actually. I'm going to show you two way of doing it. So let's start with way number one. So we're looking for a function phi, which is a two variable function, so that the partial of phi with respect to x is m, which is in this case is 3x squared minus 2xy plus 2. And also the partial of phi with respect to y is n. In this case, my n is 6y squared minus x squared plus 3. So those are the m and n given in the question. So for example, let's look at the first one. If I have the partial of phi with respect to x, how I go back to the function phi? Well, you have to take the integral of both sides with respect to x, right? So here, let's take the integral of both sides with respect to x. So the integral of this partial derivative of phi with respect to x, if I take the integral with respect to x, of course, I get back the original function phi. In this side, if I take the integral with respect to x, it's like a partial derivative, but it's not the derivative, it's the integral. So it's like a partial integral. So you're taking integral with respect to x. So x is the variable, y is the number. So let's do that. So remember, x is the variable. So the integral of 3x squared, 3 is a constant, and the integral of x squared is x cubed over 3 minus y is like a number. So this y is like you can take outside the integral. And the integral of 2x is x squared. And I'm going to copy this y plus the integral of 2 is 2x. Remember, x is the variable. Plus c, but here your c can be any function of y because y is like a number. So it's not really c, it could be any function of y. I'll call it a of y. In general, you add plus c, but in this case, it's actually more than c. Any function of y can be thought as a constant, right? Okay. So I can cancel out these three. Let me write it down. So I get x cubed minus x squared y plus 2x plus a of y. Now we have to figure out what is my a of y. Once I know that, I know phi. So let's think about that. Now we have to use, of course, this one to figure out my a of y, right? So here it says the partial of phi with respect to y is this. But I also know phi from here. So let's take, so from at this point, let's actually take the derivative of phi with respect to y. So from here, let's take the partial derivative of both sides with respect to y. Because I want to compare this partial derivative of phi with respect to y to this partial derivative of phi with respect to y. They're supposed to be equal to each other, right? So let's do that. So here I'm taking the partial derivative of phi with respect to y. So partial derivative of both sides with respect to y. So in this side, the partial derivative of phi with respect to y, let's do that. So y is the variable, x is like a number. So the partial derivative of x cubed is 0 because x is like a number. The partial derivative of negative x squared y is negative x squared. The partial derivative of 2x is 0 plus the partial derivative of a of y. I mean, a of y is a function of y only. So it's actually just regular derivative, dA over dy. And it's supposed to be equal to, look at here, I also have a partial derivative of phi with respect to y right here. They are both partial derivative of phi with respect to y. So they're supposed to be equal to each other. So this should be equal to this also because this is also partial derivative of phi with respect to y, right? So that should also be equal to that quantity here, right? See, this is partial derivative of phi with respect to y. This is also partial derivative of phi with respect to y. So they should be equal to each other. So let's set them equal to each other. So the 6y squared minus x squared, 6y squared minus x squared plus 3. So this equality must be true because they both equal to partial derivative of phi with respect to y. So from here, I can cancel out negative x squared from both sides. And look at here, the derivative of a with respect to y is equal to 6y squared plus 3. So from here, I can easily find my a of y. I have to take the integral with respect to y. So my a of y is equal to, just take the integral. So the integral of y square is y cubed over 3. The integral of 3 is 3y. Now plus c. C is the constant of integration, but I'm not going to add any c, because remember the solution of the differential equation is phi equal to c. So I can move all the c on one side and then just call it a c. So instead of adding a c here, I'm going to write equal to c at the end when I write the solution of this differential equation. So there's no need to add a c1 and then in c2 and then move everything on one side and call it a c. Just like the separable differential equation, if you remember. So I'm not going to add any c at this point. So now I know what is a of y. Okay, I can make it a 2 here. So let's write it down. My a of y is 2y cubed plus 3y. So let's write it down. My phi. My phi is x cubed minus x squared y. So let's see. X cubed minus x squared y. Okay, I can remember. Plus 2x and then plus a of y, but that's my a of y. So my solution, so now I got my phi. So the solution of this differential equation, so the solution is given by phi equal to c. So let me just copy my phi. I'm going to copy x cubed plus 2y cubed and then minus x squared y plus 2x plus 3y equal to c. It's better to write the higher exponent in the beginning as usual. Yeah, that's my implicit solution. And that's, so my y is not solved explicitly, and it is very difficult to solve because it's a cubic equation and we are not going to do that. In some easy cases you might want to make it explicit by solving for y, but not in this case. So this is my final general solution. So that's my general implicit solution. Now here you might ask, so we start with this side, this equation, and we take the integral of both sides with respect to x. What happens if I actually start with this side? If you start with this side, it does not matter, you will get the same answer. But if you start with this side, then you have to take the integral of both sides with respect to y. Let's actually do that. So I'm going to rewrite my equation here. So let's actually do that. Let me copy. Okay, maybe I can copy that one here. So let's actually do another way. Okay, it's not another way, it's like a same, but look, you start with the other equation here. Okay, so 1 second, let me add blank page. Okay, now the same question. So this is the m, this is the n, and you can think these are like way number 2. So here with the same equation, the partial of phi with respect to x is m, and the partial of phi with respect to y is n. But now we're going to start with n. So now we're going to start on this one and take the integral of both sides with respect to y. Remember, before we take the integral of this one with respect to x to recover my phi. But what happened if I start with the second one? So let's do that. Let's take the integral of both sides with respect to y. So of course, in this side, I'll get back my phi. And remember, y is the variable. You're taking integral with respect to y. So the integral of 6y square is 6y cubed over 3 minus the integral of x square is a number, is x squared y, and the integral of 3 is 3y, plus any function of x. So let's call it b of x. So b of x will be any function of x, because here x is a constant. So I can add any function of x as a constant. So let me simplify. So this is just 2y cubed minus x squared y plus 3y plus b of x. So the question is, what will be my b of x? We actually know the answer from the previous. Take a look at it. I know what is my function b of x supposed to be, right? We know that. So b of x supposed to be 2x plus x cubed. So this x cubed plus 2x supposed to be my function b of x, right? Let's take a look at it, how we can actually do it here. So now we're going to use this equation. So from here, I'm going to take the partial derivative of both sides with respect to x. So because I want to compare this with this one. So let's take the partial derivative of both sides with respect to x. So the partial derivative of both sides with respect to x. So let's do that. So on the left, I get the partial of phi with respect to x. So x is the variable, y is like a number. So the partial derivative of 2y cubed is 0, is a number. The partial derivative of negative x squared y is negative 2xy. The partial derivative of 3y is 0 because 3y is a number. Plus the partial derivative of b with respect to x is just db dx because b is a function of one variable, only x. And this is supposed to be equal to this one because they are both equal to partial of phi with respect to x. So this is supposed to be also equal to that, right? Here. So that goes here because they are both partial of phi with respect to x, right? They are both partial of phi with respect to x, so they're supposed to be equal to each other. So let's write that down. 3x squared minus 2xy, 3x squared minus 2xy. So let's 3x squared minus 2xy plus 2. Let me double check. 3x squared minus 2xy plus 2. Okay, very good. I can cancel out negative 2xy from both sides. So I get the derivative of b with respect to x is 3x squared plus 2. So the function b of x is the integral of 3x squared plus 2, which is x cubed plus 2x. So now I know what is b of x, so I can plug it in place of b of x. Again, I'm not adding any c for the constant of integration. So my final answer here, I'm going to copy everything and accept my b is x cubed plus 2x. So let's do that. So my phi is equal to 2y cubed minus x squared y plus 3y and then plus b of x, which is x cubed plus 2x. So that's my phi. It's the same phi that we get before. So the solution is, of course, you set this equal to c. So that's my solution. It's exactly the same solution as before. And finally, there's a way number 3. It's a completely different way. But take a look at it. So this will be my way number 3. Again, the same equation. The partial of phi with respect to x is m, and the partial of phi with respect to y is n. Now, instead of comparing, we're going to take the integral of both of them. So for the first one, I'm going to take the integral of both sides with respect to x. And here, I'm going to take the integral of both sides with respect to y. So let's do that. So here, if I take the integral of both sides with respect to x, I get the original phi equal to, and we did this before, so I'm just going to do it quickly. So I get x cubed minus x squared y plus 2x plus any function of y. We call it a of y. Here, when I take the integral of both sides with respect to y, and we did this before, I'm going to get the original phi equal to y cubed, so 2y cubed minus x squared y plus 3y plus any function of x, which we call it bx. So both of this integral, we did this before. Now we're going to compare. So I have a phi here and I have a phi here. So we need to compare them. Let's compare. So any common term, we're going to copy only one. Any common term that belongs to both of them. So any common term, we will take only one of them. So let's do that. So if you look at carefully, I have negative x squared y and I have a negative x squared y. So my final phi that we're looking at, my phi, let's do that. So I have a negative x squared and negative x squared. So I'll take one of them only, negative x squared y. Anything else that is not common, you have to just write it down. So x cubed, I don't have any x cubed, so I write it down here, plus x cubed plus 2x plus 2y cubed plus 3y. That's it. That's your phi. It's the same answer we get before. So let's review that. You take the integral of both of this equation. So you take the integral of both sides with respect to x, integral of both sides with respect to y, and you get these two possible phi. And when you compare them, what will happen is that the a of y, you'll get it from here. And the b of x, you'll get it from here. See, my a of y, if you look at the other one, is 2y cubed plus 3y. And my b of x, if you look at the other one, is x cubed plus 2x. So when you compare them both and write it down at the same time, you'll get all the missing b of x and a of y. So again, you just write that equal to c, and that's your solution. So we have three ways of finding the potential function phi. Always remember, you can do it. Always believe in yourself. Bye bye.